Today my topic is how to reduce the uncertainty from sensors of remote health. So I'm Atrayee Gupta, and I'm currently working on a remote health project where what we are going to discuss today. What is the overall topic? What is our main objective? What is the methodology? And some results, and of course, in conclusion. So, what my purpose is to how to collect data from patients who are remotely located from the country, and they are that is around 40 kilometers away. So normally where the doctors cannot approach. So what we did, we deployed some monitoring instruments, sensor devices, so that they automatically collect data from the patient body and then upload it to the remote cloud, where we analyze the data, where we present it to the doctors in the formidable approach. Now, the problem is normally we see in case of analog sensors, those give accurate value, and what happens to the digital sensors? They are automatic, but they are prone to errors. What kind of errors? But from several experimentation and test, we have seen that whatever sensors we are using, they have some kind of accuracy related error and some precision related error. Of course, we have checked. There were no bias errors. There were no bias errors. So what we are trying to do over here, we have developed the sensors in a certain way so that they are easily approachable from cloud. So whenever we want to instantiate the sensor, they will be accessed by different persons, like for caregivers and for doctors, for analysts. So what are these? These are software versions of the actual physical sensors. What they do, they can give easily access. They can be they are programmable in the sense they don't have to be programmed in the hardware level. What they can be done, they adds a level of abstraction so that easy management of sensor devices can be done from the software level. So this is our approach. At the lowest level lies the physical sensors, from where we are abstracting in the cloudlet as a software entities, as a virtual sensors. Then we are adding some analytical packages and machine learning packages, so that using some software modules and using another kind of and we are giving an interface so that they can be accessed, and we can do several kind of things. Different users can use these virtual sensors in their own way. What they can do, they are we can open a connection, we can read from the sensor data, when we can close the connection whenever we want. So the problem is how whatever errors we are getting from the physical sensor, they are visible in the virtual sensor also. So what we are doing here, we are trying to give a support so that this uncertainty can be reduced. So what is our approach? In the software level, we are providing here a methodology so that the sensor data can be reduced from the accuracy level can be improved, and also the uncertainty related to the precision errors also can be reduced. So how to do that? The first experimentally, we have collected a sample of a group of people. So that first group, we collected the sample in such a way so that we can develop a model. In this case, the model will be used for for improving the accuracy of the digital sensors. So we are collecting the pairs like analog sensors and also the digital sensors. We are collecting data from digital sensors. So what we can do actually, we can develop a model using as a y is equals if a function of x. In this case, x will be digital sensor value and y, which we want to get, is accurate value. So once we get this, we get a model. Then next step is for validation. In the case of blood pressure, what happens? The blood pressure changes for different person. So whatever model we develop for the first group, that is for the sensor specific only. So that will not be, that is general for all the persons. So now that's why we call it partially qualifying it to the accurate value. We get the accurate data and then we match with the person. How we match with the person? The second step is we take the BP of the person in such a way. First, we have to develop a model to reduce the precision related error. We have to develop a model so that we use this group for precision reduction. Now we collected the data for several days, and first we develop a model, then we validate. The person who gives the class of the more number of samples that the more number of samples that falls for a particular class represents the person's characteristics, blood pressure characteristics. Now this is the model for that person. Now when we measure the data with the digital sensor, then it gives a value. Then we feed into the step 1, the accuracy model, and we get the partially accurate data. Once we get the partially accurate data, we check. Once we get the partially accurate data, we check whether the value falls in any of this range. If it falls, then there is no related error. But if it deviates, how can it deviate? If it deviates for 2 or more reading, then there is this kind of uncertainty. So if it deviates for the single person, then obviously it's a medical issue. But if it deviates for more than 2 persons, then we have to replace the sensors. So what is the model which actually what we used? We collected the data for the group of person, and then we have seen that for a particular person, such as for a hypertensive person, so if the number of repeated systolic and diastolic values are found from the sample, we have studied that a number of similar kind of systolic and diastolic values are found. So this has been done for several persons. Once we get that, we kind of group them together and within an interval, so that we pair them. So systolic is paired with the diastolic value. So we get the model for the person. Now let's check. So actually for a particular person's blood pressure, it has been noticed that a range of values are seen. So when we measure with a digital sensor, VP sensor from Cooking Hacks, we get this. So after accuracy, partially after using the model 1, that is accuracy model, we get a value like this, and we check whether it falls in the hypertensive zone. Yes, it falls. and then in which interval, the interval that we studied in here, okay, that we studied in these two cases, in which interval it falls. If it falls, if it matches with a particular interval, then there is no random error is found. But if it deviates, in that is for in second case, after the modulation, the 82, the diastolic falls in the range, but the systolic deviates. In this case, what we have done, that the systolic which falls in the nearest interval is matched. So now we are matching the systolic BP. The third is, so the systolic error is reduced. Now in the third case, we see that the diastolic value differentiates. So what we have done in that case, we found actually the systolic value falls in the matching range, but the diastolic value deviates from the learned range. So what we did, we measured the diastolic interval. Within this matching interval, we have maximized it from 80 minus 5 to 90, which is the maximum limit for that person, learned from that person, plus 5. So we give another range of interval. So this, does it fall within this range? So yes, it falls within this range, but it exceeds the maximum limit. Now we are like approximating it with the maximum value. So the diastolic BP is corrected by using the systolic range. Now in the another case, which 140 by 100, which goes beyond the range for the pre-hypertensive person. So it is actually an uncertainty which has to be we have to use the previous steps again. So our the problem was how to reduce the uncertainty, and using from the digital sensors in the remote health. So what we did a interval mapping technique, so that using the learned or the behavior of the pattern of BP of the person. Now first we generalized a model for the accuracy, then we use that model to further reduce, and we also use the pattern of the person to reduce the precision related error. So both the accuracy and the precision related error are minimized using more continuous value from the range, actually by interval mapping technique. And moreover, as this approach, what we are doing over the software layer, so it is more approachable in the sense that we don't have to program. If anything happens in the hardware sensor, so we don't have to go there and then replace the sensor or program the sensor. Whatever we do, or even if we add more programming complexity in the hardware level, the sensors are like not that easily, they are limited in their capacity, in programming capacity and in memory capacity. So definitely we are avoiding that. So these are our approaches.
Thank you very much.
Thank you.